All right, so you've got an Excel assignment due Monday. Connect, I think I had set for Wednesday, and then we'll have that exam on Wednesday as well. So I would not suggest, waiting to work on that Connect until Wednesday. It's just set there just in case. Okay. Hopefully, we've got a pretty good start on both of those. If you're having any questions with those, feel free to reach out. Should be really similar to what we did in class with the contingency table and binomial function last class for the Excel, and then the Connect kind of goes back all the way to probability stuff and kind of works up through that. Any questions for me before we get going? No? I can't hear you. I'm just showing whoever was talking. All right. I really don't care. I was just being. Okay, so we did all the way up through the Poisson distribution. One thing I didn't mention, it's kind of a unique feature of the Poisson. I actually had a paper at one point I wrote that kind of exploited this, is that for the Poisson distribution, just the way it works out, oh, where's my clicker? That the mean ends up being obviously whatever the average rate is. That makes sense, right? Remember, the Poisson, this is one where we say, okay, if on average so many soldiers are killed by horses every year, right? That's going to be our lambda. So that lambda is essentially our mean. What ends up being true if we took every outcome, subtracted the mean of lambda, squared it, and multiplied it by the probability we saw that x outcome, which we get that probability just from that Poisson distribution probability mass function. We actually end up with the variance is always lambda, right? So this is a bizarre distribution that these mathematicians or statisticians stumbled across, and it doesn't matter what that average rate is, doesn't matter what lambda is, the mean and the variance of a Poisson distribution or a variable that is discretely a random variable, and it kind of takes on these Poisson properties. The mean and the variance end up being the same, and then the standard deviation obviously is the square root of that. So kind of a neat property. We also kind of get an idea of or kind of bring these two together, Poisson and binomial. We can actually think about certain situations with the binomial distribution that might be difficult for us to solve. So let's say we've got a mass that contains 10,000 atoms of a radioactive substance. Okay. The probability that any one atom decays in the next 1 minute will be 0.0005. What's the probability that I see 3 of these 10,000 atoms decay in the next minute? So here we actually have a binomial distribution. So even though we have some time involved, really what we're looking at is 10,000 atoms. The probability any one atom decays is 0.005. And we want to know what's the probability that 3 of the 1,000. So we have a cap, right? Or 10,000. 10,000 is the highest we can see, right? So our n would be 10,000. Our x is 3. And our probability is 0.0005. So just ahead of time, if we want to think about the mean of a binomial variable, it's just n times p, right? So what's the number of expected atoms that we see decay? 10,000 times 0.005. On average, we'll see 5 atoms decay. Just to kind of give us an idea of what we're thinking. So I start to plug these into my binomial equation, right? So I got 10,000 is n, so 10 n factorial. I believe it's then x factorial and minus x factorial, right? Which I can write some things out and cancel a lot, and then it becomes a little more manageable. And there's more stuff here I'm just not going to mention for a second, right? But even if I go 0.0005 to the x, and then 1 minus 0.005 to the 10,000 minus x. So take 0.9995 and try to raise it to the power of 9,997. I'm going to guess that you get an overflow error. Could be wrong, but test out to see if that's the case. It really helps prove my point. So if you took 0.9995, I'm trying to take it to the 9,999 power, or 907 power. Is your calculator able to do that? Really? Okay, so you got a nice calculator. We're still okay here, right? We can do this all on our calculator. Because we can cancel all this out, right? You can't do 10,000 factorial, but you can write this out and realize that a lot of things cancel, okay? If we didn't have as nice of a calculator, or we try to do something like, what's the probability that 50? Okay, well now we've got things, yeah, things will cancel, but we're still going to be left with enough values that it's going to be pretty big, and a lot of calculators probably still can do it. And also, it's just a pain, right? It's just a pain dealing with like these high numbers, these crazy high numbers, and all these factorials. So we can't get this entered into a calculator and cancel out in this fraction to make it actually be able to handle it. We get about 0.14. Okay? Well, I really don't like these factorials for higher numbers of successes. I might start to have an issue with being able to calculate these. So what ends up being true that as long as we have a really large number of trials and the probability of success is relatively small, which really large trials, probability is very small, right? And there's no there are actually some thresholds, but it kind of depends. As your sample size gets higher, the threshold for how low the probability needs to be gets a little bit higher as well. And so there's no real set rule, but any situation that we kind of see a pretty small probability, really large number of trials, we actually can approximate with a Poisson distribution. So instead of going through all this, writing this binomial out, I always think the Poisson is just easier to deal with in general. So instead of doing all this, right, what I can do is use my average, use my mean from that binomial, and just make that my lambda. Right? So if I make that my lambda, right, I take x is still, I want to know what's the probability of 3 decay, and on average 5 decay. Well, I can just plug that in to my Poisson distribution. Lambda is 5, x is 3. That's all I needed. That e was what, 2.71828, right? Or a stored number in your calculator. So we have the average rate of 5. We go ahead and plug that in for our lambda, and the Poisson gives us a really good approximation of what the binomial would. In fact, to the 5th decimal, it's no different than if we use the binomial distribution function. And I would argue much easier. So if we think about the visual, this kind of makes sense. We'll go back to what we were using last class. Maybe. Here we go. Right? So kind of notice when I had probabilities of 0.5 or really, really small probability, sorry. When I had probabilities of 0.5, this looks like a normal distribution. When I have really small probabilities here, the small I got was 0.1. But notice with that probability of 0.1 minus 5, so my average or my mean would be 0.5 there. I also had, we didn't do these. I had another one with the Poisson. Maybe I didn't show it to you last class. Maybe it's in the future. Hold on. There it is. When I have kind of low probability of success or low means here with Poisson, notice this starts to kind of look like what I had there with my own. Right? They're not exactly the same, right? But they're similar, right? And so if I can get something much smaller than 0.1, like really low probabilities, they look even more similar. And that's why that kind of works. You can kind of, like I said, you can kind of see it here. This looks like this really, really right skew distribution. But as that probability gets smaller and smaller, it only becomes a better and better approximation. All right, so went through this stuff, went through this example. Oops. Any questions kind of over this before we keep moving? So we can use that Poisson to approximate our binomial with a really large sample size n, really small probability of success 0.005. So which of these would be a situation where we couldn't use the Poisson? So remember, the Poisson is a certain number of successes over an interval. Usually that's time, but it can be a space interval. I'll try to give you an example of that in just a second. So the probability, the number of accidents that occur on a highway on a given day. Right? Well, if we can find the average rate, right? This is a perfect kind of a sound. We've got a time frame of the day. This one definitely is a situation where we can apply the Poisson distribution. Probability that a stock return exceeds 10% in a given year. So we see that word year. Initially, we might think we've got a time interval, everything's good. But if I think about what are my number of successes here? You know, I'm thinking about a stock going over a certain value, but that's, you know, I can't see a stock go over 10%. You know, I mean, it can go up and down, but it's either above 10% or it's not. It's not like happening. Now, if I said, what's the probability that a stock in my portfolio goes over 10, right? Where I have several different possible numbers of successes, maybe I could do that. But here I don't have any real number of occurrences. So B doesn't make any sense for us. Yep, which means the other two will. We can kind of think through them. So the probability of seeing a certain number of calls in a call center over a minute, you have the historical average, lambda, that's really all you need. As long as you have that historical average lambda and whatever interval you're looking over, you can use the Poisson. So you can also think number of insurance claims over the next month or the next year, making sure you have enough agents to be able to handle all the business. These are things that you might want to project, right? I want to know the probability that I see a certain number of, if I'm an insurance company, I really care about this, right? Or the number of accidents that I see on the work site, right? I think I might have actually used that as an example on your exam. But like the number of accidents that occur in a company over a specific amount of time. You might want to know that as a company, right? Because you have liability issues, you got to, well, you know, it's not good. So we'll do one more example, and then I'm going to kind of do something that's nowhere in the slides, so pay attention to that. And then we might introduce a continuous random variable today and finish it up on Friday. That'll be the last thing that we do. Okay, so famous example. We got this dude. He was, I forget his name, William something he said. He was hired by Guinness to be a brewer, right? And no real formal training in math or statistics or college or anything. So he comes in, he starts working at this brewery, and he's testing it, right? So like, I don't know how many of you, I don't know if any of you are 21 yet, but you can go to a brewery, you can go to a brewery without being 21. So if you ever go to a brewery, a lot of them like to like have on display like where they're brewing the beer, like these huge vats, right? They're like kind of look like silos, right? And so obviously, like I want to get a certain taste or to get whatever, I want the consistency of that liquid to meet certain criteria, right? But I can't test the entire thing, or I'm wasting a lot if I do. So I might start pulling out like a little bit at a time and like testing to see, okay, does this little amount have kind of the characteristics of what I want the whole vat to have? So maybe I'm measuring this by the number of particles, whether or not like yeast particles or something per milliliter. Right? So I take a milliliter out of this vat, I look at the number of yeast particles in this milliliter, and what I end up figuring out is the number of particles in that milliliter ends up following a Poisson distribution. So it's kind of what he discovered. I'm not saying how did he discover this, right? He's like, okay, it looks like it follows this Poisson distribution. Now this discovery, along with other ones, he never gets any credit for, and they actually just kind of refer to him as student, right? So back then, people were very elitist, right? 1899, he didn't have any formal training, like you can go to university, you know, they didn't take what you were saying seriously, although this guy was coming up with some really brilliant discoveries. In fact, we'll talk about his distributions later on the semester, the student T distributions. Right? He actually came up with them, but never gets any, didn't get really any recognition. But I don't know, he made a bunch of money, so I gave him some nice little benefits. Right? Well, we can turn this idea into a Poisson problem, and it's not time, right? I did not mention anything about time. So we're looking at yeast particles that are in this vat of liquid that we're trying to make beer. We pull out a milliliter, right? And I say, well, they agitate it so they make sure they kind of try to get a little more consistent throughout the entire vat. So I get a milliliter and I see that there are 10 particles kind of per milliliter in this sample that I took. What's the probability that the entire vat, right, that there's 8 particles? So I'm only getting one sample, right? And the kind of average that I'm seeing in my sample is 10. But I know that it's just a sample, and so maybe if I'm targeting 8 particles per milliliter, maybe the entire vat does kind of have a consistency of 8 particles per milliliter. But based off of the average that I saw from my sample, what's the probability that it has that 8? Right? Well, because I know from that one sample I took that the average yeast particles will be 10 per milliliter. But right, just because that it's the most common outcome doesn't mean that it is the actual outcome I would realize if I tested the entire vat. So what I'm looking for is what's the probability that it's actually 8? Well, here it's not time. My interval here is a milliliter. Over a milliliter, what's the probability I see 8 yeast particles? Given that the average yeast particles I've seen over this milliliter is 10. Well, now it's just a matter of plugging in lambda and plugging in x is 8, right, into our Poisson. Right, we kind of mentioned that this Poisson distribution. No plumbing shove, no pun intended there. So sometimes I try to sneak these in that figure fun. But so we get this 0.11, right? So if I'm the brewer, this could be an issue where I'm like, look, based off the sample I'm seeing, the probability that my target yeast per milliliter, so that this beer tastes the way I want it, it's only 0.11. Right? This might be a concern. We might have an entire vat that we just wasted all of our resources on, right? And we can find the probability of 8 or below, or we can find all these different things by simply kind of plugging in different x values into our Poisson and getting the probability of seeing those different number of occurrences there. But this is a really unique one. I won't give you something like this on the exam, but I just wanted to give an example where the interval doesn't always have to be time. You can actually do space, like a milliliter of liquid, a mile of road, but those are hard to deal with. I've forgotten some of the conversion rates even, so we're not going to deal with any of that because the next thing I'm going to show you, it would get even harder to do if we weren't using time intervals. Okay? So I think that should finish it. Yeah, next thing is continuous random variables. Oh yeah, have you heard the joke about the Poisson distribution? It's pretty fishy. I think it's like Poisson is fish in French. Yeah, there we go. I didn't make this. I found this and thought it was very applicable. So that's why it's in there. All right. What did I look up this morning? It was the number of people. Oh yeah. So the number of people in Indiana who die. Wait, no. Was it 15? No, it was not 15. The number that died was only 5. So on average, every year in Indiana, 5 people die in a car accident with deer. I hate deer, right? For that very reason. They're annoying. They taste delicious, but I hate them. They're not good for society, right? So they cause a lot of damage, but they kill 5 people, and that's just in Indiana. Right? So let's start to think about, this is how many people they kill every year. What if I wanted to do, what's the probability that this next year, or not next year, sorry. We'll do next month. What's the probability that 1 person dies in Indiana from an accident with a deer? So I've changed the time interval. Right? Now, my example might not be perfect because I'm sure that the likelihood of hitting a deer is different across different months. But for the sake of this example, assume that it's constant throughout the whole year. Right? A little bit of an assumption there, but we'll think we're all right with that. So how can I use the Poisson distribution? Right? I've got time intervals, I've got the average rate, but I want the number of successes in a different time interval. So if I ever have a situation like this, what I need to do is find the average rate for whatever time interval I'm interested in, right? So I need to know the average month. So if we assume that every month is equally as likely, and if 5 people on average die every year, what would the average rate be for 1 month? Yeah, 5 over 12. So anytime and now it's just a matter of my lambda is 5/12, my x is equal to 1, plug everything in. Right? So anytime I want to go to a smaller time interval, right? So I'm going from a larger to a smaller time interval. Anytime I'm making that kind of transit, I would take the larger average rate and divide it by something, right? So I'll call this some factor, right? For us here, it was 12, right? Depends on the situation. I want to go from an hour to a minute. Well, I'm going from a larger time interval to a smaller time interval. So I'll take my old lambda and I'll divide it by some factor. If I go from an hour to a minute, I'll take the average rate over an hour and divide it by 60, right? So this is going to always depend on what we're looking at. Now, the examples that I will use on the exam will only ever be like things that I think are pretty obvious. I might even state very obvious things like there's 12 months in a year, there's 7 days in a week, just to make sure like, that could never be some confusion. Now you can imagine we could do similar things with like going from a mile to a yard, right? Or something like that. It just, the factors get a little bit messier, right? So once I have my new lambda, though, everything's the same. So really the tricky part of this process is just figuring out what my new lambda is. Right? But once I have that new lambda, I've already got that x I would need. Now it's just a matter of plugging into that Poisson distribution equation. What if I wanted to go, how many people die, I don't know, in the next 5 years from deer accidents? Well, anytime I'm going from a small to a larger time interval, I'll take that old lambda and I'll multiply it by some factor, right? So anytime I'm going to a larger time interval, I'm going to multiply my old lambda by some factor. Here, the factor is kind of easy, right? If I'm going from 1 year to 5 years, I would just multiply it by 5. Right? So this is kind of the, maybe writing this down, kind of keep it straight. Anytime I'm going from a large to a smaller time interval, I'm going to divide my old lambda by some factor. Going from a small to a larger time interval, I'll multiply. And that kind of makes sense. Like if you're thinking about like, if you ever like mixed them up, let's say I was doing this and I accidentally divided. So I divided by 5 and I'm like, okay, so 5 people on average are killed every year. 1 person on average is killed every 5 years. I mean, that doesn't even intuitively make sense, right? So, you know, anytime we're going to a larger time interval, our lambda should be getting larger, so we multiply it. Anytime we're going to a smaller time interval, our lambda should be getting, our new lambda should be smaller. If we divide by, you know, anything above 1. Then, yeah. Any questions over this? Okay with this one? So yeah, that's the only other kind of wrinkle that I could be asked to encounter. I would say, I don't know, hopefully it's becoming a little bit like, this is a pretty relevant, probably mass function. Like you would use this a lot, like the number of customers you might expect based off of historical averages, you know, the number of, I don't know, the number of items purchased from an individual based off of what you usually see when someone comes into a store, the number of employees that will leave your company based off in the next year over based off historical averages. Like these are all things that could follow the Poisson distribution. So it's pretty useful, pretty applicable. You'll see it pop up a lot. All right. So let me think how I want to do this today. We've got about 20 minutes left, 25 minutes. So I showed you guys the binomial Excel stuff last class, correct? I just want to make sure okay, I wasn't remembering correctly. So those are 2 specific types of discrete random variables we've talked about, binomial Poisson. They're probably the most useful. We're now going to leave the discrete world. Okay, we're going to live in the continuous world for like the foreseeable future, right? So if we're looking at continuous random variables, we're going to have to start to have some issues, right? So, you know, we have this, the number line, right? I can see the values in between now. We can do annual income, interest rates. We've already thought about these things. So I'm going to have a probability density function for a continuous random variable as well. The problem is I can't find the probability of any one value. And I'll set this up in the most basic way ever. Okay? Let's assume that I have a variable where every outcome is equally as likely. That's my probability mass function. Okay? So my probability mass function is that everything is equally as likely. Right? Every single outcome is 1 over however many possible outcomes I have. The issue is if it's a truly continuous random variable, how many possible outcomes are there? Yeah, even between 0 and 1, it's an infinite number of possible values. So 1 over infinity, right, which in the limit approaches 0. So we have a problem, right? With a truly continuous random variable, my probability mass function, even the most basic one, can't give me the probability of one specific value. Okay? But what I could do is if I think about, right, there's an infinite number of possible values in between 0 and 1. So the probability of any one value in this range is 0, right? 1 over infinity. But what if I asked you, what's the probability that I see the outcome be greater than or equal to 0.5? Well, that's half the space, so that probably is actually 0.5. I can find the probability of intervals here, right? But I can't find the probability of one specific value. Kind of counterintuitive, but I mean, this, I think, hopefully kind of sets up, right? There's an infinite number of possible values in here. So the probability of any one value is 0, but I know that half of the space between 0 and 1 would be between 0.5 and 1. Right? So we can find the probability over intervals. And we can put it in graphs and tables now. Instead of doing these bar graphs, we get to deal with some nice continuous lines, right? So that things actually look like a function now. And, you know, we'll write this kind of f of x, and we'll, you know, this is our function, our probability density function, f of x, whatever our x variable is, and we can find the probability over different intervals. So this function, right, is still telling us a probability. Now it's a probability over an interval, but even so, what's the smallest or largest that probability should be? 0 to 1, yeah, right? The highest it should be is 1, the lowest it could ever be is 0. Probably more likely somewhere in between this, right? Now, let's think about what's another condition. Actually, I jumped the gun. I thought I did even expand pieces, right? So one thing we can't have with our continuous random variable is we can't have like jumps in the function, whatever it is. So we can't have that. We said that it has to be between 0 and 1. I put above 0 there, but really we can put a cap on it as well. One of the things we had with our discrete random variables, if I took the probability of every outcome, I know they have to add up to 1. The same idea applies. Let's say I've got this nice continuous random variable, so I can draw it out as a function. If I take, right, I'm thinking about, if I could do this thought exercise, very like calculus, right? If I took like infinitesimally small intervals, I can't find the probability of any one value, but I can find the probability of like really, really small intervals, and then just added them all up, right? We'll take the area under the curve. They should all add up to 1. So this is why, like, if I could integrate that probability mass function, that value would be 1. The area under the curve is 1. They still do that when I teach it, right? Like the little rectangle that like missing out on little pieces, and it gets me back to school. I didn't care and really didn't have any idea what was going on. So it's very similar to what we're doing with discrete random variables. Now we're just thinking about the area under the curve has to be 1. Okay? So I always draw usually a continuous random variable as like a normal distribution, kind of this bell curve. It doesn't have to be. We'll introduce today a uniformly distributed random variable, which looks nothing like this. But you know, the area under any continuous random variable will always be 1 for us. Doesn't matter if it looks like a normal distribution or something a little bit different. We can do a cumulative density function. which is the same idea as what we're doing with a discrete random variable. It's just going to tell you the probability that you see that X value or anything below it. Right? So as I get really close to the largest values, the probability I see the largest values or anything below them, it's really close to 1. Cumulative density function for really low values of X will get really close to 0. So it'd be like, when I'm thinking about the distribution for income, the cumulative mass function for, the value of 500, probably still makes 500 or less, pretty close to 0. The probability that for a cumulative mass function, if I'm looking at, 300,000, the probability that someone makes 300,000 or less is really high, right? Most everyone, right? Other than the real lucky. So we can start to think about visually with these continuous random variables, what we're going to be doing, right? And how we're going to write this. So if I wanted to write what's the probability that X is less than or equal to a certain value A, what I'm going to use, and I thought I had it up here in the slides, maybe I do, but we're going to use kind of this capital F to represent the cumulative. Oh yeah, there you go. All right, so the probability that X is less than or equal to A, it's like if I could plug A into my cumulative density function, that cumulative density function would take the probability of every single value below A and add them all up. Okay? So we're going to start writing kind of a cumulative density function, the probability of seeing this value or anything below it, as like capital F of A. So if I wanted the probability that X is greater than B, using kind of this idea of a cumulative density function, how would that be written? Well, the cumulative density function always tells me the area to the left, right? Or probably seeing that or anything below it. So if I want the probability of being greater than B, right, I could just use that cumulative density function. It would tell me the probability of seeing B or anything less. Right? If I want the probability that I see B or anything greater, it would just be 1 minus that cumulative density function. Does that make sense? And we don't really have to worry about the equalities as much with continuous random variables, which is really nice, because like saying X is greater than or equal to B, this is like a real mind something. So I want to do, I can actually prove that the probability that X is less than or equal to B is the same as the probability that X is less than B, the continuous random variable, right? So I can break this down, right? I could technically rewrite this. And let's say, I'll just give you a value to make it a little bit easier. Let's say B was 50. I can find the probability that X is equal to 50, equal to 49.99999. Right? If I could go through every single possible value, and they're mutually exclusive still. I'm only going to see one value when I actually finally see it. So I could break this down and say this is actually the same thing as the probability X is equal to 50 plus the probability X is less than 50. Still includes all of the values in this range, right? Everything below 50 and then the exact value of 50. Every number is accounted for when I rewrite this way. Right? But if I have a truly continuous random variable, what should the probability of X being equal to 50 be? So I can actually prove the probability of X being less than or equal to 50 is the same as being less than 50. And that's only because we have a truly continuous random variable, right? If it wasn't truly continuous, kind of all bets are off. So that was just my way of pointing out. We don't really have to worry about the equalities as much, so that's nice. Okay? What if I wanted the probability that I'm between A and B? Right? Using a cumulative density function, how would I find that? Remember, the cumulative density function tells me the probability of seeing that value or anything less. So if I want this, right? Yeah.
Find the cumulative function B and then subtract the function A.
Perfect, right? So what that's going to do visually is I'm going to take the probability of seeing B or anything less. So I'm going to draw these as horizontal lines. That's represented by that area. If I then subtract from that the probability that I see A or anything less, I subtract out this area, right? Wherever they overlap, that kind of cancels out. So I'm just left with what's in between. That's really all that cumulative density function is doing. It's finding the area to the left of A, area to the left of B, subtracting that smaller area from the larger area. Any questions on that? So, we could do other things, right? We could then take that and subtract it from 1. That would give us the area of the tails. We can start playing around with this, kind of like these different areas underneath the curve, once we have this idea of the cumulative density function down. But this will become a little more about this for now. It'll become a little bit more obvious as we start working with this uniform distribution. Okay. We might be able to do a louder review on Friday. So I'll bring in those practice exams. Have looked at, that's fine. I'll just start working through some problems I think are important. So the uniform distribution is this really unique continuous random variable where every outcome is equally as likely. So what that's going to tell us is that wherever our maximum and our minimum are, right, that's going to give us the range of possible values, right? So if everything's equally as likely, it should be that you think about it. If I had, I'll do an easy one first. So if I went from 0 to 10, right, excuse me, if every outcome is equally as likely, then if I'm thinking about my probability being over here, kind of on that y-axis, that's going to look like is this horizontal line, right? The probability I see something between 0 and 1 is the same as the probability I see it between 1 and 2, same as the probability I see between 3 and 4, right? All those areas will be the same. Why? Because they're basically just the area of rectangles, right? Once I figure out what this height should be, the area from 0 to 1 is the exact same area as from 1 to 2. Now, how do I determine the height of this distribution? Right? If I look at the difference between the maximum and the minimum, right? Any one outcome we'll think about, the probability of saying that would be just 1 over that range of possible values. Now I chose 0 here, it makes it a little bit easier, but if it was from 20 to 10, it would still be 1 over 20 minus 10, right? So maximum minus the minimum. So D here is our maximum, C is our minimum. And if it's any X value outside the range of our minimum and maximum, the probability is just 0. So this is like, I don't know, kind of, I don't know why we have to, say that, I guess, to be like kind of complete, right? Everything outside the range of our minimum and maximum is going to have a probability of 0. Right? That's what that 0 otherwise means. So our probability density function for this uniformly distributed variable is going to end up being this, but I'll show you a slightly easier way to think about it. So let's say I wanted to find the probability that this X value over here is somewhere between 9 and 10. Right? Well, I could plug everything into this probability density function where A and B are the beginning and end of my interval I'm interested in finding the probability of. D and C are just the maximum and the minimum values, which here B and D end up being the same value, but that's okay, they can. Right? I can plug all my values in there and it'll spit out at me the correct probability. An easier way to think about it, I think, I'm just going to find the area of this rectangle, right? I know the height is 1 over 10 minus 0. So height, I know the base or length, however you want to call the length, width, base height is, so I already have the height. The base goes from 10 to 9, or the width, right, is 10 to 9. So that's just going to be what? 1 over 10. Now I could have plugged everything into that equation, I end up with the exact same thing, but really all this is the area of a rectangle. Okay. Now notice, what if I wanted the probability that's between 1 and 2? What's the only thing that changes? I still have the same height. but now going from 1 to 2, you get the exact same probability. And that's because every equally sized interval will have the same width and the same height, right? So the kind of area underneath that curve, even if the curve here is a flat line, will be exactly the same. And then to kind of prove to ourselves that the area under the curve, which is not a flat line, will be 1. So if I want the entire area under the curve, what I'm really saying is take the width of my rectangle, so 10 minus 0, multiply that by the height, which is 1 over 10 minus 0. No matter what minimum maximum I choose here, I'm always going to end up with that area under that curve. That area in this space, this rectangle, will always be 1. Questions kind of related to this idea of the uniform distribution? All right, so this is kind of a nice visual of kind of how every uniform distribution should be kind of set up in terms of you can always determine what the height is by 1 over the maximum minus the minimum. You always know where it starts and stops, right? Whatever your minimum and maximum are. And then it's really just looking for different areas of rectangles, right? So we'll do a lot more of this on Friday. I'll skip this. See if you've been listening to me, and I'll go back and work on those. All right. So let's say, and like I said, we'll use this example again. Santa with Muscles is a movie. Just believe me, it actually exists for now. I'll show you some screenshots from the next class. But let's say we have this kind of demand for popcorn at a movie theater, right? So it can be anywhere from 1 to 10, right? 1 to 10 pounds. What's the probability that exactly 9.5 pounds are going to be demanded, whatever day this is, whatever day the movie is playing, right? So I've got, instead of 0 to 10, 1 to 10 is my uniform distribution. So I can figure out my height of that distribution. But I want to know what's the probability of exactly 9.5 pounds of popcorn, but not less than 9.5, exactly 9.5. So if you're listening to what I was saying when I was setting up the idea of the continuous random variable, this one should be really easy to answer. Right? You can actually plug in everything to the formula and still get the same answer, but it should be really easy to answer if you were listening to kind of some of the discussion earlier. Think about, we're looking for the probability of one specific value, which is the probability of 9.5. And this is a truly continuous random variable. Okay. Go to that 2-minute mark and we'll talk about this one. All right, you haven't gotten an answer in. Take your best guess. We got what, 4, 5, 6, 7, 14 people. All right, make sure you get a response in. I'm going to close it out. Just 11 of us here today. There should be missing one person. Are we good? All right, I'm going to close it out. So, what should this probability be? Yeah, 0, right? I said earlier, the probability of any one value is just 0. If I want the probability of exactly 9.5, my interval starts and stops at the same value. So if my interval starts and stops at the same value, what would my values for A and B be? A and B, right? The same thing, 9.5. So then when I go ahead and I start to plug in, ignore this, so I'm just using it as 9.5 minus 9.5, 0 divided by anything is 0. I'm always going to end up with 0. I'm looking for the probability of any one value. Right? So I really want to kind of hammer that point home that we're looking at intervals. We'll work on finding a few more intervals next class, some other characteristics of the uniform distribution. Kind of wrap that discussion up. Probably, I'm guessing, will take us 15, 20 minutes, right? But we'll use the second half of the class to then kind of go over some exam review. Okay. All right. I will see you guys on Friday. Okay.
I have a question.
Yeah.
That's like, since we're taking a